Hello, this is Professor Ramsey, and in this recording, we're going to discuss variability, and there'll be a second follow-on recording. And I'll be using the notes from Understanding Variability that are available on Blackboard. As I said in the opening of the course, Six Sigma is primarily about variation reduction in a process. So in this section, we're going to define what we mean by variation and give various definitions of it. And again, the key point here is to understand the concepts of variation. Although we use the term, often we're a little bit fuzzy in terms of explaining it. Okay. And I'm going to start with a demonstration of variation using a tool called the quincunx. And this was developed by a scientist named Sir Francis Galton in the 1800s. And Galton developed a device to try to demonstrate to other scientists the concept of a distribution. That is, most scientists didn't understand the idea of variation in his era. And they just assumed that if you made a measurement, you could put a great deal of importance to that one single measurement. And Galton, among others, began to explain, well, no, one single measurement may not necessarily have a lot of interpretation because all of these measurements are subject to random variation, or today most people just call it noise. So I'm going to switch over to a little device. It's a virtual quincunx, and it's a nice way of explaining what we mean by variation. Okay. So by the way, it's called a quincunx because the pattern of the pins you see at the top of the display, and the pattern actually looks a bit like an ancient Roman coin, that a five-sided coin they called a quincunx. So that's where the term actually comes from. And the idea of the quincunx is that I drop a bead from a funnel and it goes down through the rows of pins. If it hits a pin, it's got a 50-50 chance of going in either direction. So as it hits the various pins, collectively, it can follow many different paths. Basically, this is the idea of what we call random variation. Every time we make a product or we deliver a service, there are always a series of events that take place in the system that perturb that service or that product, so that the products are never quite alike. And in fact, in highly variable processes, there can be a great deal of variation. As an example, the time it, say, takes you to travel to work from your home, even though you take the same route every day, the times are different. Why? There's so many different events that can occur. Maybe weather, traffic, construction, any number of delays. You may stop for coffee at a drive-through and it takes longer than it usually does. But you get the idea. And each of those events is a bit like a pin. It perturbs your time to drive home. Same thing if you go into a restaurant and you go there frequently and you discover the service is highly variable. Sometimes it's very good, sometimes it's very bad. And by the way, customers usually remember when it's very bad and they may not come back. Again, there are many elements within the restaurant that could have caused that variation. And again, that's what these pins represent. So to illustrate, I'm going to drop a bead. This funnel is centered at position 16. Okay, so I know that because this is a simulation. Notice I dropped a bead and it followed a path through the pins and it landed at 16. So can I now assume that this process works perfectly? In point of fact, I can't make any statement about that observation at 16 unless I understand what we call the distribution of possible values the location can take on. So let's drop a second one. Slow the animation down slightly for you. Notice it's not taking the same path. So this one seems to have landed somewhere around 20. So you said, yeah, around 20. Should I do anything? In other words, I want to hit 16, I got 20. A tendency we have as people is to try to do something about it. But what I'll show in a moment is neither 16 nor 20 are unusual. Every time I drop a bead, I'll more or less get a different path. So here's a third one. This one landed at 14. Again, a tendency we would have as a person is to say, well, I wanted to hit 16, I hit 14, I better move the funnel. Something's wrong. But again, all three of these measurements, there's nothing unusual. They're all the product of hitting the pins in different locations and being given a different path. This is what we mean by variation. There are things within your system that cause variation in the outputs. And part of Six Sigma is figuring out what those sources of variation are and trying to fix them. So let's drop another bead. It landed at 20, or I drop another one. So what you see is I'm starting to get some scatter or spread in the locations, and what will happen eventually if I drop enough beads, you'll see that there is a whole distribution of possible values. So when we talk about a distribution, we mean just that, the overall pattern of variation that occurs. So what I'm going to do is reset the quincunx and take off the animation and drop a lot of beads. So I'll drop them 10 at a time. So I'll just start dropping them. Notice as we drop them, a pattern is developing. So here we've dropped, I don't know exactly how many, but 360. Notice, on average, we want it to hit 16, and we have. But notice the variation tends to run between 10 and 22. So by gathering a lot of data or observations, I begin to know something about how this system behaves. I know that the distribution of locations is mound-shaped. Okay, it's centered somewhere around 16, and the total variation runs between 10 and 22. In other words, as long as my beads are falling in the range of 10 to 22, there's nothing wrong with this system. This is how it behaves. So what we're going to learn in the near future is how do we characterize these distributions so we can use them to describe the behavior of some process or service that we're studying. The key point right now is, because I've made all these observations, I can at least tell people, well, you're going to get values between 10 and 22, and that's perfectly natural for this process. So each, say you're buying products, the value or characteristic of your product could vary in this range, and if that's not acceptable, then you'll have to do something about the process. The key to this is to realize that these pins at the top represent variation. In many ways, they represent real-world events that cause variation in any process or service. They happen all the time. And in fact, in a moment, we're going to call these common cause variation because the pins are always present. Okay. So I'm going to reset the quincunx. And I'm going to go back to dropping one bead at a time. Well, suppose I didn't really understand the concept of process variation. In other words, there's a certain amount of noise or inherent variation in the process. Now that we've got a whole distribution of measurements, we know what it is, and we can at least tell people what to expect for variation in our products that we deliver to them. Well, suppose I don't really understand that, so I drop a bead. Remember, I wanted to hit 16. So I say, oh dear, I've hit 19. I guess I better move the funnel. So I move the funnel 3 places to the left. 1, 2, 3. I figure there must be something wrong, so all I need to do is tweak that funnel. Well, you might be tempted to think, well, now I can't miss being at 16, but let's see what happens. Oh, no. I'm at 15, 14, 13, 12, I'm at 11. I've got to go 5 to the right. There, now I've got it tweaked in. I should be able to hit 16, so I drop a bead. Oops. I'm now at 17, 18, 19, 20, 21, 22. Ooh, I've got to go 6 to the left. Leave that 6. It'll serve the purpose anyway. Oh, I'm getting better. I'm at 14. So we'll try it again. What? I moved the funnel just right. I should have hit 16. Now I'm way down at 11. I've got to go 1, 2, 3, 4, 5. Hey, I hit 16. I've got this figured out. Ooh, wait a minute. I hit 15, 17 on the next one. I better tweak it a little bit. Oh, wait a minute. I hit 14. What's going on here? Okay. Well, as you can see, adjusting the position of the funnel so I can get closer to 16 is actually making the situation worse. In other words, the more I move the funnel around, the more variable things get. And we're going to talk about this in a moment because I mentioned W. Edwards Deming. Deming called this tampering, and tampering is a natural human, let's say, urge to try to fix things without really understanding cause and effect. So in tampering, what one would do is keep trying to move the funnel around as a way to make things better. In other words, to reduce variation. People do this all the time. They're just hopeless tamperers. They have some ideal performance they want. They don't see it. They start changing things. Professional athletes are often victims of tampering. They have a bad at bat, a bad hole in golf, or bad set in tennis, and they suddenly start playing with all their mechanics, and pretty soon they're lost. People who manufacture products and deliver services are doing it all the time, hopelessly overreacting to what turn out to be nothing but natural outputs for the system. So I'm going to reset this again. So the question is, as long as I'm centered at 16 and I keep dropping beads, as I said, we're going to see a range of variation of say 10 to 22. So how could I reduce the variation? Well, the fact of the matter is, moving the funnel around, the most obvious thing to do, won't help. But remember what I said, these pins represent sources of variation in a system. Well, what if I remove some of the pins? So just to illustrate, I'm going to remove half of the rows of pins. I do that by simply aligning them. 10. And then I'll drop a lot of beads, and let's see what happens. Although I think you can figure this out pretty quickly. Notice I'm centered at 16, but now my variation is roughly from around 12 to, let's see, 17, 18, 19, 20. I've reduced the variation. How have I done that? I've eliminated sources of variation. Now, if I kept going and removed, say, all of the pins, then I'd hit 16 every time, because this is a simulation. And the whole point, what's key about this, the whole point of Six Sigma and also Lean is essentially finding the symbolic pins or sources of variation in the system, eliminating it, at least some of them, and reducing variation. Now, in an actual process, we don't have pins, but we do have sources of variation. And unlike the quincunx, we're going to discover some of them cause more variation than others. So our primary goal is going to be how to figure out or find those sources of variation. And typically they're going to require collecting data or analyzing data and the use of statistics. So at this point, I'm going to reset the quincunx. And go back over, I'm going to put this on slideshow, and talk a little bit about what Deming called tampering. I'm going to introduce some terminology, but I'm going to come back to it later, in fact, a number of times in the course. Deming described the variation in two ways. He said all the variation you see in a process of whatever, using a process in general, it could be making something, it could be delivering a service, falls into two buckets. One he called common cause, the other special cause. Basically, common cause means sources of variation that are always there. They're always at work in the system. Think of the pins in the quincunx. We call the pins common cause variation because they're common to the system. Again, people today often like to think of it as noise or background noise. It's always present. But there's another source of variation. This is not inherent to the system. This is something unusual that happens on occasion. And Deming called it special cause. In fact, before him, a man named Walter Shewhart, we'll talk about, and we've mentioned in the introduction, called it assignable cause. In other words, common cause variation, it's very hard to understand the causes because there are many of them. Special causes are unusual events. For instance, I mentioned driving to work. Well, one day you're driving to work, you get a flat tire, and that really upsets your time, or maybe you get stopped for speeding. Well, for most of us, that would be a special event, not part of our daily drive to work. So we call these special causes, and we'll talk more about those in a little bit. And again, we'll refer to them many times in the course. Well, we often use the terminology in control or stable. If a process is in control, that means the only variation we see is a result of common cause variation. In other words, it's inherent. There are many words for it. Inherent variation, common cause variation, noise, all of them mean the same thing. But we say the process is stable or in control. For instance, the quincunx, I drop a lot of beads and I don't touch the funnel and the variation goes from 10 to 22. We call that stable. In other words, the total amount of variation is predictable. In other words, because those common causes are always there, always present, I can't predict where each bead will fall when I drop it, but I can tell you it'll be between 10 and 22, And most often it'll be around 16 because I know what the distribution looks like. Okay? So basically, if you have a stable system, you're not going to improve it by superficial measurements or adjustments. Remember how I moved the funnel around and you could see even in 5 or 6 drops, I was increasing the variation. Well, Deming had a word for it. He called it tampering. Making superficial adjustments to a process when common cause variation is present. Okay? And in his book, Out of the Crisis, he did what he called the funnel experiment. And I was going to have you watch a YouTube video, but if you go and search YouTube, you'll see an actual video of Deming doing what he called the funnel experiment. And I'll show you, and it's mentioned in his book, Out of the Crisis, I think his second to last book. I don't ask people to read it. Deming wrote in a very, how do I say it, dense and somewhat hard to comprehend manner. There's a lot of substance, but you have to work to extract it. So Out of the Crisis is considered one of his best books. So I'm just going to illustrate what he would do in real time. He'd take a table, he'd put down a sheet of paper with a target and a bullseye. Then he'd take a funnel and he'd position the funnel so it was right over the target, and he'd drop a marble. Marble would come down, hit the target, roll to a stop, and wherever it stopped, he'd make a mark. Okay? So suppose I dropped a bead. Okay? And it fell here. Okay? Well, what do we do? Well, Deming would say if it's an in-control process, we do nothing. That's exactly how that process works. But what he said is there are 4 basic strategies. There are actually probably 6 or 7, but 4 strategies which we could use to try to get closer to the target. In other words, our goal on average is to get our beads or marbles to come to rest closer to the target. So he said there's 4 common things that you can do. Okay. Rule number 1 is do nothing. And by the way, this is the optimal strategy. Do not adjust the funnel. Okay. Rule number 2, he called exact compensation. You saw me doing this with the funnel. So with the quincunx, moving the funnel for the quincunx, I dropped a bead. I wanted 16. I landed 18. So I moved the funnel 2 positions to the left. That way, so instead of being centered at 16, I'm at 14. People for instance, over the years that work in machining often call this adjusting to 0. And by the way, many of them are hopeless tamperers. So if I drop a bead, I want 16, it lands at 18, I would move the funnel 2 positions to the left. Now if I drop another bead and that bead happened to land at 14, I then move the funnel 2 positions to the right. In other words, I'm always moving the funnel in an opposite direction toward the target from where the marble came to land. Okay, that's very common, and we're going to show, you can actually mathematically show, we won't do it, it's not trivial, that by using exact compensation, you increase the variation of the process 40%. And that's well known. Overcompensation is you to actually figure out where the bead lands, you take the funnel and you move it an opposite direction from the target. In other words, I don't just move the funnel 2 positions. So if I landed at 18, okay, or let's say I landed at 20, I would take the funnel, put it at 16, and then I would move it in the opposite direction to 12. It's called overcompensation. This strategy means, well, I was way on one side of the target, but by golly, that's not going to happen again. So I move it farther, an equal distance in the opposite side of the funnel. Overcompensation is very common, and as you're going to see in a moment with a simulation, it has catastrophic consequences. And then the last one is called consistency, or the make the next one just like the last one. What you do in this strategy, if you drop a bead, suppose it lands at 18. Well, I'm going to give up on hitting 16, but I'm going to be really consistent, so I move the funnel exactly to 18. And then I drop a bead, convincing myself that all the drops will now be at 18. I think you've seen enough to know that just ain't going to happen. In fact, what consistency leads to is wild variation, and statisticians call it a random walk. In other words, your process or service walks away. And I at one time worked for a company that used the consistency strategy to make a product, and despite my best efforts to convince them that it was a bad idea, they kept on doing it until the product became so far from its targets that their major customer called up and said, your product absolutely doesn't work and you better fix it in a hurry. The problem is there's no simple way to fix it. You've wandered all over the place making adjustments. There's no way to know how to go back to where you started. Okay, so I'm going to show a simulation, and this is a little jump program. You actually have it. And I'm going to show you the strategies. So rule number one, I've centered the funnel at 0, 0, and these are like 10,000 drops. Notice the tight little circle. That's no adjustment. We just let the marbles come to rest wherever they may be. Exact compensation is to the right. Notice the diameter of the circle is bigger, and it's actually 40% bigger. Notice these two strategies, though, on average, I do hit the funnel, except the second one, on average, I'm farther from the funnel. And then let's go down to overcompensation. And notice, in fact, if you do simulations, these tend to take on rather fascinating visual patterns, almost like a Rorschach test. But notice what's going on. On average, I'm hitting the target. But wow, look at the variation. It's exploded. Look at the scales of measurement, okay, for Rule 1 and Rule 2. Now look at Rule 3. So by overcompensating, we've driven wild variation. And by the way, companies do this all the time. In fact, organizations. Suppose in one quarter they have a huge backlog, so they start producing a great deal of goods, trying to catch up, and they finally do. So in the next quarter they say, well, we don't want a big backlog, so they make a big increase in manufacturing for that quarter, but sales go back to normal. Pretty soon they have a large inventory. They have a large inventory. They say, oh my God, we better cut way back on manufacturing. And they just ping pong the organization back and forth between backlogs and high inventory. I've seen them do it with personnel. We're slow this quarter, so we're going to lay people off. The next quarter, you discover you don't have enough staff, so you start hiring, and then you go through cycles of hiring and laying off, hiring and laying off. That's all overcompensation. It's a failure to understand that you're going to see fluctuations in customer demand in business. It's very common. And then this last strategy, look at it. We don't even hit the target, and we just start wandering away. And as a random walk, this, in theory, could go to infinity. But what typically happens, within a relatively short period of time, your service has gotten so bad or your product so bad that it just stops. In other words, the process stops. Nobody will use your product. It is so bad. You've wandered so far away. And I have to assure you, this is all a reality. This happens all the time. Tampering is the number one cause of excessive variability in most organizations. Hopelessly tampering. I worked with a health insurance company at one time, and it seemed like every medical claim that came through was a new adventure because management kept changing the process all the time, reacting to some event last week and running out and changing the process. So it seemed like they were never stable, they were always in a state of flux, and all they were doing is just driving more and more quality problems in the process. So one of the things you will have to do first in a continuous improvement project is to stop the tampering. In other words, you've got to get everyone on board with doing the process or the service in the same way. Once we stop the tampering, then we can start addressing the common cause variation. Okay. And to summarize from out of the crisis is the following summary. If anyone adjusts a stable process, meaning only common cause variation, to try to compensate for a result that is undesirable or a result that is extra good, the output that follows will be worse than if he or she had left the process alone. Bottom line, if you have a stable or in control process, superficial adjustments in reaction to the outputs only make the problem worse. And depending on the strategy you use, as I just showed, with exact compensation, you'll increase your variation 40%. By the way, I have seen that in actual practice. With one company, I told them, you're constantly tampering and doing exact compensation. They stopped doing it for 2 weeks and their variation dropped 40%, causing the CEO to almost have his head explode because he said, I can't believe what we've been doing to ourselves for 2 years. We were causing all that variation and we didn't realize it. So if it's a stable process, you're not going to fix it by just reacting to the outputs. And with Six Sigma, we assume that as we delve into sources of variation, that we've brought the process to a stable state, or we could say in control, and statisticians sometimes say a stationary process. The amount of variation is predictable. Okay, so remember the rules of the funnel and the lessons of tampering. Trying to make superficial adjustments can and will make it worse. In Six Sigma, we're not going to react to the outputs. We're going to study the inputs, and we're going to fix the inputs causing the variation in the outputs. Okay.